Okay, good afternoon. I think we can start. So it's a great pleasure to have Professor Caterina Vernieri at Brown here for the colloquium. So Caterina obtained her PhD at from Scuola Normale Superiore in Italy in 2014. So he crossed the Atlantic and she went to Fermilab for her postdoc, right? And then in 2018, you went even more west, right, at SLAC as Panofsky Fellow. So before she was working in CMS, at SLAC she moved to ATLAS. Nobody's perfect, but c'est la vie. And in 2022, you were promoted to assistant professor of physics, right? And among many highlights is that in 2021, you obtained the DOE Early Career. You were awarded the DOE Early Career Award. So, yeah, today you are going to talk about delving into the unknown, using the Higgs boson as a tool for discovery, I guess, right?
Yep.
Okay. So, thank you very much again. It's a great pleasure to have you here, and we are very excited to hear the talk. Thank you.
Thank you. So I'm very happy to be here today to tell you a little bit more about things that I found exciting in the Collider world. I'm very happy to be at Brown and spend a very great day talking to many of you. So I hope you will enjoy this digression into why we really care about the Higgs boson and why we're so excited about understanding it further. So to put things into context, you probably are very familiar with this chart, which is very humbling. It basically tells us that what we can observe in our universe right now, we can always explain a very tiny fraction of it. Most of it, it's dark matter and dark energy whose interaction and origin are pretty much unknown. We can only explain the 5% made up of the ordinary matter, and even there, we cannot really explain everything, and I'll walk you through a little bit of it. So everything we can explain related to ordinary matter is encoded in what the so-called standard model theory that is telling us which are the building blocks of matter and how they interact with each other. So this table here is our version of the periodic table of the elements. It's the particle physics version of that, and characterized the building blocks, which are quarks, that make up protons and neutrons, and then make up the nuclei of the atoms. And then we have the leptons, not just the electron we're familiar with from the atoms, but also like their heavier replica, the muon and the tau, which are heavier and more unstable. And these particles, neutrino, that don't really interact with anything, and they exist. We know them from beta decay that they exist and they carry some energy, but we have yet to really characterize, even understand their mass. And they interact with each other. The charged ones, they exchange photons. That's our way as particle physicists to explain electromagnetism. The quarks, they are bonded together from the gluons. They are responsible, the carrier of the strong force. And then we have the electroweak interaction, again, the beta decay, which is mediated by the W and the Z bosons. So this is our way to characterize particular fields and the exchange interaction by exchanging bosons. And the one thing that was missing from all this was how they actually acquired mass in a way that the theory was still valid. So we're not going to get more in detail about it, about how in the theory you have to add an Higgs boson, but like you need it in order to give mass to the particle. And we knew it, that the only way to be, an elegant way to give mass to the particles in the standard model was through the Higgs field. But there were no evidence of this particle, the Higgs boson, until 2012. And there was a major milestone in particle physics and collider, especially, when both ATLAS and CMS announced the discovery of this particle. And the theorists that actually had postulated the existence of this particle and the mechanism of the electroweak symmetry breaking, like almost 50 years prior, got the Nobel Prize for it. And I'm sure you heard about the Higgs boson discovery and a lot about it. So what I'm going to tell you today is how, after more than 10 years, the Higgs boson still plays a central role into our planning for the future of collider physics, what we have learned and what we still don't know. So first, let me just spend a minute here. So what is the Higgs boson? So I told you the particles are filled. So the Higgs field is very special because it's always on, permeates space and time all the time. The source of the Higgs field is always on. You can think of like electromagnetic wave is activated when you turn on your radio. Like we don't know how to turn off the radio of the Higgs boson. The Higgs field is always on, permeates all universe, and particles are slowed down with interaction with the Higgs field. And the more they are slowed down, the more mass they gain. So the stronger the interaction with the Higgs field, just the larger the mass they will acquire. That's in a very simplified way, a way to visualize the Higgs field and why it's so critical. And why like the origin of the Higgs field is pretty much still not understood in our theory. And that's what we want to understand by studying the particle as a result of this field. So we only study Higgs bosons at Collider. That's why there's a lot we can learn about nature by other probes. But if we're really interested about the Higgs bosons, then the only way to study it is a collider. So at LHC, which is Large Hadron Collider in Geneva, we collide protons. And it's, at the moment, the largest, biggest, most energetic collider we have. It's 27 kilometers underground. So if you land in Geneva, you won't see it. It's underground on the border between Switzerland and France. And now it's colliding protons at 13.6 TeV center mass of energy, which is many order of magnitudes above the mass of the proton. So we are accelerating the protons well above their mass so that by special relativity, we know we can convert kinetic energy into mass. So we can produce heavier particles at LHC. And that's the idea that has really pushed particle physicists to go at very high energy collisions with the idea that the more energy you have in your center of mass, more particles you can produce that are massive. And that was the idea behind building LHC to find the Higgs bosons and possibly new particles. So CMS and ATLAS are the two general purpose experiments. There are two more that I'm not covering here because they are doing other interesting physics, but it's not directly related to Higgs. So CMS and ATLAS, to me now, they look like the same in the sense that they both do an amazing job at reconstructing the debris of the collisions of proton-proton interaction and collecting large data sets to study interesting things, and in particular Higgses. So the graph I put here is just to brag about how much data we have now. So by each color is a different year, different data taking, but the machine is going so well that now we have collecting 1 year what we have collected basically in 3 times more than we had collected in round 1. So we have about half inverse autobarn, which is, for many of you, doesn't mean much, this unit to measure, but it's basically the equivalent of 50 times more data we had at the time of the Higgs discovery. So, and that's like a big chunk of data we have now to really go in detail and dissect all the properties of this particle and see if it's really what the standard model looks like. So before I show you some highlights of those results, I want to spend some time telling you about how we do this at LHC. It's easy to say. We have detectors that reconstruct the debris of the collision, but there are a lot of steps into this process, and I want to give you some images and some steps about how we go about it. So here, of course, this is a concept. It's not a real picture. So it's more of visualization. It's not as accurate. But you can see like these 2 balls of fire, actually probably a proxy of packets of protons that are colliding, accelerating almost at the speed of light. And they're going to collide head-on at the center of this cylinder. And you can see there are different layers in different colors. So our detectors, our experiments, are organized with a cylindrical symmetry around the beam pipe to analyze and reconstruct all the particles you produce after you break the protons. You have the quarks and gluon interacting and producing some particles. Let's say you produce high Higgs boson, and then you produce a bunch of other particles. You want to reconstruct all the particles that are coming out of this incoming collision, and they're all different properties. So we have different layers to reconstruct different particles depending on the nature of their interaction. So already this will be standalone a series of seminars because there are a lot of reconstruction techniques that are going into analyzing those hits from each layer. and then having a combined analysis. So one thing you see, if here I have one Higgs bosons, decays promptly, and I reconstruct the final state. This would be already complicated. But in reality, it's more complicated because LHC, we don't collide one proton at a time per second. We collide 1 billion of protons per second because we have protons in packets. On average, 50-60 bosons will interact, 50-16 proton will interact at each bunch crossing, at each interaction. And we do that 40 million times per second. So overall, you have multiple proton-proton collision in the same bunch crossing. So your events are actually have a lot of particles out of these other small interaction as well. And you have to reconstruct them all to identify where the Higgs was produced. So overall, the task is even more complicated because you have to deal with very dense environment. And so this is out of CMS. Those of you working on CMS will identify the event display here of a real event from LHC. And we usually look at the transfer region, which is one orthogonal to the beam pipe. And those event display are actually beautiful. Like people working at LHC, they like them so much that we made sure that we're part of a banknote in Switzerland. This is an event display of a Higgs event. So this is a lot of the things we produce at LHC. Most of the times are just other quarks or gluons. 1 in a billion time collisions, we actually produce a Higgs boson. So let me give you some details about how we go about it. So first of all, the graph. So you see that this is a function of the center of mass of energy. What I told you earlier, right? That we need more energy, higher probability of making something more, a particle that is more massive than the proton, right? So the probability of producing a Higgs boson increases as a function of the center of mass of energy. So that's why we wanted to go high energy. We started at 8 eV at LHC, now we're working at 13.6, hopefully 14. It's an incremental, but still a little bit more energy. So, and all the lines there increase as a function of the center of mass of energy. Then each line corresponds to a different production mode, and each production mode, it's a way for us to test the Higgs interaction with standard model particles. So the idea is that I have different production modes, different way to produce Higgs bosons at LHC, either by itself, through an indirect loop with fermions, or through W fusion, so through an interaction with W and Z bosons, or direct production with the top-anti-top pair. So the idea is that I have different production mode that I can use to test the standard model prediction of the Higgs interaction with other standard model particles. And that's one way that we do to characterize the Higgs boson, really verifying that as predicted by the standard model, the probability of each of these processes corresponds to the theory. More importantly, we also test how it dies, how it decays. I mentioned earlier that Higgs boson is produced and directly decays. So then it really dies promptly in our detector, and the Higgs boson mass is a free parameter in our theory. So right after the discovery, then we measure the mass of the Higgs very precisely, and once the mass is introduced into the theory, we can exactly predict all the branching fraction of the Higgs, all the interaction of the Higgs with all the other standard model particles. So we can derive precise prediction for all the branching fraction. So for the Higgs at 125 GeV, then it mostly decays to big quarks. And then the least popular decay is to gamma-gamma and muons. And ZZ for leptons is also very tiny branching fraction, and tau-tau is somehow in the middle of those. So experimentally, each of these decay channels is a challenge. So either because the branching fraction is too low or because the signature is very challenging in relation to the background I showed you earlier. So if I were to really simplify here, just to give you a sense going forward into the talk of this branching fraction, the K modes of the Higgs as mapping into detector resolution versus signal significance, it's basically what I show here. So the discovery channels that were like there with the highest sensitivity when we observe the Higgs boson, and one can even argue that CMS and ATLAS were actually built to reconstruct muon very well. CMS has an M that stands for muon, so it was really designed to look also to Higgs for muons. It was the ZZ for leptons, mostly driven by the muon channel, and gamma-gamma. And those are very clean channels, despite the small branching fraction, where you can really explore the small resolution, experimental resolution, since the natural width of the Higgs is very small, to really identify a resonant peak on top of a continuum background. Other signatures, like B quarks, tau leptons, W decays that involve missing energy from the neutrino are more challenging. And I'm going to show you and convince you why in a second. And they also have the largest background. So keep this in mind. We will talk through this for the rest of the talk. But it's important for us to really, I want to give you really the importance that for successful measurements at LHC, we really need to understand our detector better. And when it comes to the future, in designing future detectors, now that we know about the Higgs, its mass, and its favorite decays, about keeping this in mind for detector requirements. So, not to be dramatic, but we often like to say each other at the LHC word that looking for a Higgs boson candidate event at the LHC is like looking for a needle in a haystack, because we have a lot of, like 40 million per second collisions at LHC with a lot of pileup, and only once in a billion we made a Higgs boson that decays promptly, and these signatures in the decay are very similar to other backgrounds. So it is very challenging. But over time, both CMS and ATLAS, I believe this is a CMS plot, have really improved their understanding of the detectors and how to calibrate and how to really measure things very precisely. So this is a beautiful beautiful measurement of the Higgs boson mass. So the Higgs decays to 2Z. So if some of you are trying to do the math, one is off shell, and the both decays to 4 leptons. And then you reconstruct the 4 leptons mass as a proxy of the Higgs mass. This channel has the lowest background. So if you look at the invariant mass of the 4 leptons, you can see the nice peak of the Higgs at 125 GeV, and next to it, very well separated, the peak from the Z that you can use for calibration. So right now, if you combine the ZZ to 4 lepton and the gamma-gamma channel, you have both ATLAS and CMS are claiming a relative uncertainty on the Higgs boson mass less than 0.1%, which roughly corresponds to 100 MeV. So this is a very big accomplishment from both experiments. And since this is an input to the theory, you need to know the mass this precisely in order to be able to trust then your calculations in the standard model, given the fact that the mass is an input to the theory. So moving on, I mentioned that we need to learn and measure at LHC all the production channel, the decay channels, to really test how the Higgs interacts with the standard model particles. So this plot is the result of several measurements of cross-sections and branching fractions, and combined together in a way that you have on the y-axis the measured strength of the interaction of the Higgs boson either to a fermion or to a boson, and as a function of the particle mass. So I tried to tell you earlier when we had the first nice picture of the Higgs field, conceptual picture of the Higgs field, that the strongest is the interaction, larger is the mass of the particle. And within the experimental data that we have so far, we have been able to verify this proportionality of the Higgs mechanism in our data. So it looks like the Higgs is doing exactly what it's supposed to be doing in the theory, and there is no discrepancy there. What are the caveats? Not all the measurements have a very small uncertainty. Some of them actually have a very large uncertainty, like the coupling to the muon is only known to 30%. B and tau also have an uncertainty which is bigger than 15%, and so on. Charm is not there. And actually, I would say that all the coupling of the Higgs to second generation quark has not been tested. So there is room here for new physics, or additional particles that might interfere in the electroweak sector, so these two lines of the standard model Lagrangian, that are parameterized interaction of the particles with the Higgs field that can hide new physics. And that's what we are after when we say that we want to improve and trying to achieve higher precisions in Higgs measurements. It's really to bring this uncertainty down to sub-percent, to really be able to exclude that there is no new physics contribution in the Higgs sector in these two lines of the standard model Lagrangian. In addition to that, if we really single out the Higgs field potential, the shape of the potential in the standard model is very simple. And why has that shape? It's not something that we can explain from first principle. This is the simplest form the potential can have in order to realize the electroweak symmetry breaking. But other forms are possible, and there could be more minima. And we don't know why it has to have this shape. And as physicists, we don't like when things are not explained from first principle. So the Higgs boson potential is one of that, and that's why right now, let's see, we're really chasing these measurements and trying to see if we can find new physics in this particular aspect of the electroweak sector. So if you expand, so how we test this experimentally. So once you do your electroweak symmetry baking and you expand around the minimum, you are left with a trilinear and quadrilinear term in the Higgs boson that basically are giving you prediction for Higgs pair production mediated by Higgs boson. This is a self-coupling term, so we usually call it self-coupling. And this is completely well determined once you fix the mass. So once the mass is measured, then you can predict how big the self-coupling should be. So it's very small. It's 10%, and that's something that translates into the fact that we produce once in a billion collisions, let's see, one Higgs boson. Once in a trillion, so 30 more, we produce two Higgses together that would allow us to test the self-coupling. So it's a very challenging measurement, mostly because it's statistically limited. But this is another important measurement trust about Higgs physics, about shedding light about it. There are connections with the vacuum, if it's stable or metastable, depending on the value of the self-coupling. It's connected very well with cosmology, depending on whether or not the value of the self-coupling is compatible with the standard model or not. We might have a first or second order phase transition that might explain or not, depending on the case, whether or not how we have the anti-baryon asymmetry. So we have been told, we experimentalists have been told by the theory community, we need to aim for at least 20% or better precisions on the Higgs self-coupling in order to be able to exclude with very much certainty, we call that 5 sigma, electroweak baryogenesis model. So one more challenge, and then I'll show you some cool images after this. It's that we don't just produce two Higgses at LHC through the self-coupling interaction. We also have them through a loop of fermions. And those two diagrams kind of interfere with each other in a way that is maximum. So that's why the cross-section, the probability of producing two Higgses is very tiny at LHC. And moreover, they have a very interesting different kinematic properties, these two processes. We are not that sensitive to really measure that, but we know that if we could, then we could disentangle new physics contribution by looking at the mass distribution of the two Higgses. So the idea is that we know how much it should contribute each diagram. We know how much should contribute interference. If there is new physics that is actually entering into the Higgs potential and changing any standard model prediction, I should be able to also test it in the Higgs mass. And that's something that experimentally, as we gain some more sensitivity, we really would like to do. So the kind of events we are looking for are this. This is a candidate event where allegedly one Higgs is produced and going to two photons, and another one is produced and going to two big quarks. So now let me tell you finally how we do that with ATLAS, but CMS is doing similarly, if not better. So first of all, our experiments are big. I've shown you pictures. ATLAS is even bigger than CMS. It's basically 22 meters diameter, like those two people are there for scale. You have the incoming beam in the picture we saw before, and then you have all these different layers, and I will explain you now what they are. And you have the collisions, and then you reconstruct all the particles are going through. You want to have magnetic fields, because charged particles in a magnetic field, they bend, and depending on the bending, we can identify if they are positive, negative, and the momentum. For comparison, ATLAS is a 5-story building tall. CMS is more compact, and is a little bit smaller. Different design choices, similar performance at the end. So now, take a section here where the beam is coming out of the screen, and let's look into one slice, each component at a time. So you have your collisions, you produce some particles traversing through this slice of your detector. So closer to the interaction region, you want to have very high granularity. It's where you have the most particles close to each other. If they're charged, they're going to leave some tiny deposits into silicon layers that we place on top of the interaction region. The first layer usually is at 3 centimeters from the interaction region. And then you put these hits together, and you're able to reconstruct the trajectory of your particle. And that's one way for us to measure their momentum later. Then electrons and photons will be absorbed in the electromagnetic calorimeter that is placed afterwards. And then all the particles, hadrons that interact only with a strong interaction, will be absorbed into the hadronic calorimeter. So almost all the particles then are contained into the calorimeters, except the muons, which traverse all the material, leaving very tiny energy. So we have usually also CMS has the same additional tracking devices outside the calorimeter to keep reconstructing the trajectory of the muon and precisely extract their momentum. So this is a nutshell. A couple of things I have not said here is that when we produce other quark and gluons, usually they tend to trying to get into a stable place, having additional gluons being radiated so that they can recombine into stable particles. And then what we measure in our detector, it's a spray of particles, stable particles clustered very close to each other. So we reconstruct them as jet. So a quark or a gluon in our detector will look like a spray of particle that we call jet, and then we will tell you how we identify the flavor of these jets, depending on the flavor of quarks. Neutrino go through, so we extrapolate the energy by imposing conservation of the momentum in the transverse plane, but we don't really reconstruct neutrino. So this is what we have to deal with. So we read out our detector as fast as we can. We say all the information of each of the subdetector. And then we know that each particle will have a different image in our detector. So the photons will only be absorbed in the electromagnetic calorimeter. So I only expect an imaging into the electromagnetic calorimeter because they're neutral. Electrons, I expect also something in the tracking. So the image is different, and so on. So for neutrons, for instance, which is made of quarks, only it's neutral, only interact with a strong interaction. I would see a little bit in the electromagnetic calorimeter, but mostly into the hadronic. So we put these images together, and then we reconstruct particles. So I go into my data after I've been combined all the algorithms I've been running in order to tag the event with the list of particles that have been produced at each event. And I ask for 2 photons. And this is not really out of the box. Again, here from CMS, ATLAS is similar. You can see the beautiful reconstructed, beautiful peak at 125. The Higgs has no natural width. This is all experimental resolution. It's very tiny. It's at the level of less than 2 GeV. So this is a beautiful Higgs to gamma-gamma simulated event. Now, let's go to the next topic. How identify B quarks? So here it's a little bit more convoluted because there is more physics to put together in order to do that. So a B quark mostly produces a B hadron, and a B hadron has a sizable lifetime, and usually 500 microns, but usually these B hadrons, they carry some momentum. So if you add the beta gamma from a B quark from a Higgs boson decay, a 50 GeV, then it gets to 5 millimeters. And we can measure 5 millimeters displacement in our detectors. So the idea is that we produce our B quark at the primary vertex of interaction. Then this hadronizes, the B hadron is produced. It travels into the detector a few millimeters before it decays. So the idea is that you look for in your spray of particle, in your jet, if a B hadron is being produced, then in the jet direction, you will see another cluster of particle from the B hadron decay. And our algorithms now have got so efficient into identifying a secondary vertex from the B hadron decay and achieve very good efficiency for it. So I'm showing now ATLAS results, but CMS has done achieving similar performances. So the idea is that you look for all the tracks that charge particles that look displaced with respect to the primary vertex, including all the information from tracking, and then all the possible information about secondary vertex and so on. And you combine that with particle transformers, like the most sophisticated neural network we have now available on the market, that really combines this information for us instead for us to calculate observables as we used to. And this is really allowing for us to inject as much data as possible into these models and for them to do the selection for us. What we used to do before is to apply some pre-selection, to have identified a good, clean samples of candidate tracks that maybe were associated to a B hadron, and then having to build in some observables and feed that into a neural network. Now we're giving to a neural network, because the models have got so sophisticated and good at it, a lot of raw information, and that has led to a very powerful increase in efficiency. So if I compare with what we had just 5 years ago, these new models have been allowing us to have a 4x improvement in rejection at fixed efficiency. So CMS has provided similar improvements by using the latest model. So then, in a nutshell, what we do, we get information from the calorimeters, from the tracker. This is 2 candidate jets. And then we know the theory. We inject that in our model. We train simulation, and then we return with an algorithm that is telling us 90% probability with very tiny 10 to the minus 3 mistag probability this is a B quark. And then I trust, and then I select my B quarks, I label my images, and then I can look, for instance, 2 candidate events where, again, I have 1 Higgs to 2 photons, 1 Higgs to 2 Bs, and looking for events where I can look for di-Higgs. This is a very new result that is using the data from 2024, which means an additional 170 inverse femtobarn with respect to the previous year. So this is combining run 2 or run 3 now. And a lot of data. This is not the final data set that we have, including 2025 data. But so it's not the large number I said at the beginning. It's a bit less, but still almost a factor 2 more data with respect to run 2 alone. And we can go and look for di-Higgs to be big gamma gamma. This is our latest result. This is the diphoton mass. So we basically apply some selection to try to have a very high purity signal enriched simulation with 2 Bs, 2 photons. We apply a lot of kinematic selection that I'm saving you from. I just want to show here that once you look then at your data to extract your signal, now you have to worry also about the single Higgs background. So we are looking now for signals where the single Higgs background is a background for our signal extraction. And just to give you some pointers, like by using the latest B-tagging algorithm with all the improvements we can get from the latest AI models and more data, we have been able to improve with respect to the previous iteration of the analysis back factor 5. So analysis is scaling faster than just adding more data, simply because as we add more data, we are also becoming more sophisticated in our analysis tool, and we are taking the most out of it. And I'm always amazed in the fact that I'm working on an analysis where the single Higgs now is a background 10 years after the discovery. So, and of course, that means we are going to go after and look at simultaneous extraction of single Higgs and double Higgs in the future. Now, where were we? So we're still taking data. You here, Brown, are building some parts for the future upgrade of CMS. SLAC, we're building also the pixel detector for the upgrade of ATLAS. So we're all busy building detectors for the upgrade for ILLUMINATE-C, with the promise that ILLUMINATE-C we will get factor 10 more data, so a lot of more Higgs pair produced, and the possibility to really observe this process. And it's a long way through it. In order to get high luminosity, we'll also have to deal with increased density of pileup. So I was showing you images before that was with 50, 60 proton-proton collision piling up to at every branch crossing. For ILLUMINATE-C, we will have to deal with 200. So that's a lot of tracks to reconstruct in what it is, 10 centimeters interaction region, which means the only way to cope with it is to build detectors that are more granular. And that's what we're doing, both CMS and ATLAS. So let me show you just a little bit, since I'm biased because I work on this. At SLAC, we're building the pixel system, which is the first 2 layers at 3 centimeters from the interaction region. And in order to be able to be competitive, because if you get more data, you also won't be able to keep the same physics performance, otherwise you're not gaining in your measurements. So having more data comes with the responsibility to really be able to be very excellent at particle reconstruction. So in order to maintain the occupancy of per mean level so that we can distinguish tracks that are produced close by, we have to improve the granularity, more pixels. So it's basically, it's like we're going from 10 to the 6 channel to 10 to the 9 pixel channels. So it's a very large increase in resolution. And of course, radiation is another concern. Everything has to be radiation hard. We are at the phase where we are done testing with prototypes in 3D printed parts. This is one NCAP for the pixel system that we will be built as SLAC and then shipped to CERN. I don't know yet how, but the idea is that we will airship to CERN for installation. So if we do well in building our upgraded detectors, and we can keep the performance that we assumed when we did this projection, then the idea is that we can go to 2 to 5% precisions to most of the coupling. So this is an updated version of the plot I showed you earlier with the run 2 and run 3 data. This is with the projected sensitivity for 3 inverse autobarn ATLAS alone. So you can expect that you can combine ATLAS and CMS for better precision. But still, 2 to 5, it's not the sub% precision I was claiming we need. And charm is not in this projection. Here, you guys, some of you, Lucas Group is working on X2CC, so I expect at a certain point we can try to assess how well we can do. But still, it's very challenging to distinguish charm from bottom quark at HC. So the systematic error will be a dominating uncertainty. And like UCAVA, strange, is totally out of reach. But for the self-coupling, the latest projections are showing us that we can do better than we thought we could. So I told you how adding more data to the BB gamma-gamma analysis was definitely important to improve the sensitivity, but we had also other improvements going into the analysis, new algorithms, better algorithms, that allowed us to make out a more sophisticated analysis. This is what I'm showing you in this chart. So one in 2020, we did these exercises of projecting our sensitivity into the future when we were going to have more data. We based our assumption to the sensitivity of those analyses. But now our analyses are more sensitive because they're more powerful, more sophisticated. So we have updated our projection last year. And so far, it looks like we can now observe the Higgs boson, the double Higgs production. Each experiment will be able to do that with the full statistic of ILLUMINATE-C. And then if we look at what we learn from double Higgs to the self-coupling, of course, it's not a one-on-one thing because when we measure the cross-section, we measure the cross-section of the combined processes. So the uncertainty on self-coupling, it's a level of 30%, which will reduce the uncertainty on the shape, but still probably, hopefully, we will find a big discrepancy when we will be at that point. Then what's next? And still, a lot of model won't be excluded. I'm sure there will be still some theory that will be left on hold with more data. What's next? in parallel with this projection, we're also evaluating what else is going on at LHC. We have not heard of another particle being discovered at LHC, and that might suggest that new particles, if they exist, are higher mass than it's the central mass of energy reach for LHC. So I mentioned that there is room for new physics into measuring the couplings of the Higgs. So this is one example I have to convince you that's the case. So these are two simulations of how an additional scalar or an additional doublet will interfere with the projected sensitivity on the coupling of the Higgs boson to the standard model particle. So let's say you have an additional scalar or an additional doublet, and you propagate what you expect the coupling of the Higgs is, let's say, to the big quark on the charm. Then the deviation you expect from this additional particle is at the level of few percent. And depending on the model, you have other deviations that you have to measure. So this is one example to show that basically, depending on the new physics and the nature of new physics, we might expect very small deviation in the Higgs boson coupling, and by the partner of the deviations can tell us a little bit about the underlying theory. So I probably too biased about this, but I got convinced that looking at precisions and aiming for percent and sub-percent precision on the Higgs boson couplings could teach us about the scale of new physics and the nature, the kind of interactions that we expect. And it's a different environment. So ATLAS is a very clean environment because they're already fundamental particles when you collide them, so you don't have to worry about the additional quarks and gluons that you get from smashing the protons. So you have a very well-defined initial state, and Higgs bosons are produced once in 100 events instead of once in a billion, so you can actually very fast collect a lot of statistics in a very precise and clean environment. So for comparison, this is a Higgs event at LHC. You have a lot of particles, not just the Higgs particles final state, but also the underlying event, piled up, and so on. And this is LHC, not even LHC. And then ATLAS, the only particles in the final state are the particles coming from the Higgs decay, more or less. So it's a very clean environment, aided for precisions, where we can really aim to go well beyond the systematic limitation from LHC detectors. Of course, it's a different interaction, different way of producing Higgses. And now, if you look at the x-axis, we're starting from 250 GeV and up. So it's a different scale with respect to LHC because this is already fundamental. It's a different way of producing Higgs boson. So once you start operations at 250 GeV, you mostly produce Higgs boson through associated production with a Z boson. That's a very cool measurements we can do at ATLAS with this production mode. I'll come back to it. Then as you increase energy, you also have W fusion again, which is interesting in case you want to cross-check anything that you measured with the ZH. Higher energy, you have again TTH. So that's why recently after SNOMAS, we have started suggesting to run a 550 GeV because you can gain factor 2 in sensitivity by 50 GeV because you have a very sharp rise of the TTH cross-section as a function of the center of mass of energy. And then double Higgs, if we're still looking at the self-coupling, if we're not happy with what LHC can do, you have to go high energy, above 500 GeV and beyond, to really access double Higgs production. So, and in order to do that, we have just updated our projection just to tell you the kind of perspective you can have. Let's say I told you 30% at Illumine HC. Here you can do 10% with 550 GeV and a lot of data. And I can come back to this if there are questions later, but basically the idea is that you can test with very good precisions because the interference of the diagram is of a different nature, the kind of sensitivity to new physics contribution. So if there is a new physics contribution, you can actually have a better sensitivity to non-standard model value of K lambda as opposed to HC, which is the only sensitivity is quoted for the standard model value. So I'm running out of time, and I really want to tell you a few more things before my time is out, but we can go back at it in the questions. So E plus C minus. For proton-proton, I showed you a ring. And that was easy to plan. So for E plus C minus, we have choices, and that's why we have not decided yet which one to build. We have either you can go linear, where you can basically collide your bunches and trains in one shot, and so you don't recirculate the beam, but then you can go very high energy because you don't suffer from synchrotron radiation, but you only have one interaction point. So people in the past had been planning for having one detector, one interaction point, of course, but two detectors to alternate with push and pull to share the data set, just for cross-checking and the usual redundancy that we like to have in our experiments. Circular collider, you can go very high luminosity, but then you have synchrotron radiation, so you're limited at 360 GeV, more or less. And but you can have multiple interaction points of experiments that are sharing the luminosity, as we do at LHC with CMS and ATLAS. So FCC is the plan A from CERN at the moment. The decision, the process for deciding is still ongoing, but it's clear that CERN is pushing very strongly for a 100-kilometer collider that would collide electron and positron at 90 GeV to collect a lot of Z boson and do a lot of very cool electroweak measurements. And then 240 GeV for the Higgs program, and 360 GeV for additional measurements at high energy, in particular for W fusion and TT bar and so on. There was another similar collider in China, but China decided to put on hold their plan and wait for CERN. And then it was a linear collider. A lot of proposals over the years. ILC in Japan, CLIC at CERN, Cook-Copper Collider came out as NOMAS. All of these have converged together in a linear collider vision that it's put together a plan for a proposal linear collider at CERN, and might be the plan B for CERN, maybe, we don't know. So the one thing it's really cool if you ever get an E plus C minus collider to study the Higgs boson is that when you produce, you have E plus C minus interacting, producing a Z that radiates a Higgs boson. You can do something very cool here, opposite to HC. You can measure the Z, and then you can reconstruct the Higgs without assuming the branch fraction. So you can do a very model-independent measurement without any assumption on the Higgs width, Higgs decays, and so on, very agnostic. And you can do that leveraging the fact that you know very well the initial state, so you can measure the incoming energy of the electron and the positron. You're only limited by the beam energy spread, but that's at the level of per mil. And you can simulate very well beam straddling energy loss. So basically, you reconstruct the Higgs through the recoil mass now, because you know the center mass of energy, you can control that very well. You can measure very well the Z, and then you have everything you need to extract the Higgs. Now, the trick is you can do that if the precisions you have to measure your Z to mu, for instance, matches how well you measure the beam spread. And this is giving our detector requirement on momentum resolution. So this works if we can really measure Z to mu, so the muons PT, very well. And it's giving us a challenge to achieve that at detector level. So if you do that, and this is what is assumed into these results from future collider studies, don't get tricked. This is no data. This is simulation, where you see signal in background simulated, and you can extract the Higgs mass from the recoil mass at the level of 4 or 5 MeV. The results from LHC I was very proud of to show you at the beginning was 100. So here we have very good precision. And this is the kind of precision you can unlock at the plus C minus. You can really give you the percent uncertainty on the couplings and possibly discrepancies that yield to new physics hints. Another thing you really want to do is to discriminate B quarks and C quarks very well. And in order to do that, you want to be as close as possible to the interaction region. So the impact parameter resolution, which is what we use as a proxy, because we want to measure tracks that are displaced with respect to the primary vertex. So the impact parameter resolution is dominated by how granular is your detector, how close is to the interaction region, and of course, how much material the particle is seeing that like confuse and like affect the trajectory of the particle as it traverses the material. So all of this is achieved if you are very close to the interaction region, or people are discussing things that are 1 centimeter, 1.2 centimeter from the interaction region. At LHC, we are at 3.3. So it's very close to the interaction region, really gives you a good advantage to distinguish charm from bottom. And then you want to have very low material budget, very small pitch. So this is improving also with respect to LUMHC. We are very proud of improving the granularity and going to 20 micron pitch. For future colliders, we need 15 probably. So need for new generation of ultra low mass tracker with dedicated sensor design. And the challenge starts now. We might not have a collider yet, but it takes years to really deploy new technology and show scalability for a large size detector. One more caveat is that I did say it was a very clean environment, but I did miss to say that we have beam straddling. So you have, as you have electron and positron beams converging to the interaction region, you have beam straddling photons that can be radiated there, and then in turn they can interact with the incoming beam and produce additional particles. So most of the times we produce ink current per production, but it's not a negligible fraction of the time. It's 20% of the time we actually produce hadrons that go into the calorimeter. So we're worried about, the beam straddling, and it's always a trade-off about how you increase the rate of your collisions by improving the luminosity, by really squeezing your beams, but also increase your beam background. So it's always, if you're interested in improving the performance for flavor tagging, this really affects the design of the vertex detector, because larger is the beam background contribution, more particles you will see in your vertex detector, spoiling your resolution. So it's machine detector interface, and it's way more intertwined at ATLAS and CMS Collider than it is at LHC, and something to keep in mind as we develop the vertex detector design. This is just a cool image from like the SID detector, just one detector for ATLAS and CMS Collider. And you see there are rings and there is a battle region. So how you optimize this in order to have good performance and in relation to the backgrounds is something to start studying early on as you develop your collider. So we don't have to go through the table. It's basically just summarizing what I just say in a very more condensed way. And I want to mention that a material budget is also a concern. This is a plot shows for the ALICE experiment at CERN, the material budget of their very light vertex detector. And, we are really trying to reduce the size of the silicon and make it as thin as possible to reduce the material of our vertex detector, so in turn improve our resolution on the impact parameter. So at LHC right now, for ILUMI, we're installing sensors that are 100 micron thick. We think we can do them 30, 50 micron, so that could be possible. But even with that, which is what is here, you still have a lot of material in your detector you want to get rid of, and mostly are the cables. So those of you working on detector at LHC, they know that you have the sensors, but then you have a lot of cables because you have to bring power, you have to take the data out. How we can do serial powering, optical conversion, as well, optical powering as well. It's really an area of R&D that is important for future colliders to really have achieved these ultralight mass vertex detector. And one promising technology everybody is excited about is so-called MAPS, which is monolithic active pixel sensors. So it's basically a technology that has the promise to really solve some of the issue of granularity and material, because they can be tinned. They don't need for bump bonding, because now your ASIC, as in this picture here, is in the same wafer as for your sensitive layer. So everything is in one layer. You don't need to bump bond ASIC to the sensor as you do for ATLAS and CMS now. So without the bump bonding as a constraint, you can do that you can devise cells that are much smaller in pitch, so you can improve the resolution there too. And the idea is that eventually they are lower cost too, because it's an industrial process in one step. So it effectively should also save money if you're thinking of doing a lot of square meters of detectors. So this is how they look like. There is a lot of work going on at LHC for the experiment ATLAS about it. So you can thin them so much, you can bend them and wrap around the beam pipe. So it's not a done deal, because these detectors right now, they work, but they do not have a great yield. And for the precision that we need at E+C- Future Collider, we need every single tunnel to work with a very high yield and very much smaller resolution than what is done now. So I hope I've convinced you that E+C-, yes, looks great, but it's also very challenging detector-wise, and there's a lot of technology that has to go into detector development now in order to be able to take advantage of the future data. This is a very schematic view of what I showed you for ATLAS of a detector. So we have, the silicon at the beginning, then calorimeters, then the muon system. You might think, of course, you have to decide where you put your solenoid. CMS and ATLAS have a different choice about whether in or outside the calorimeter. And then you might want to have a timing layer, where you put it, how much resolution. So these are all discussions we are doing now, using Higgs physics as a benchmark for precision. And depending if you add more things, then you spoil also you spoil your material. Depending on the choices you make, you ended up with a more costly calorimeter, a more costly solenoid. So there are a lot of optimization where even AI can help us a lot to disentangle these parameters and really help us guiding where to focus for key areas of R&D. And physics, of course, is the standard model candle to really identify the key parameters for optimization. So this is a very kind of rough timeline. We are taking data now at LHC for another year. Then we are going to prepare for LHC. And the Higgs coupling precisions will improve over this time. But if we want to go to sub-percent and percent level, then we might want to have an E+C- later. And that is in the bulk of 2050s, 60s. And in the meantime, if we really want to go to high energy, really see new physics eventually, we really need to identify a key technology that will take us there now and work on the most promising technology. FCC-EE, as the current plan goes, should start operation in 2047. And we will stay tuned to see what the community will decide, what the government will decide about the contributions there. So I want to conclude here with this plot, this image, before I go to my conclusion. We put it together here around 3 years ago at the end of a meeting about the energy frontier. We were trying to capture, with one slide, one image, the importance of the Higgs boson to convince people outside the collider community why it was so important to study the Higgs boson. So I hope my talk gives you some anchor point of why we really care about the Higgs bosons at colliders, why after 10 years of the discovery is still a subject of study and is helping us planning for the future colliders. It's the only fundamental scalar we have in the theory, and it's very connected to a deep question about the universe and its evolution. And we can, of course, we can address some of these questions elsewhere too, but we can only study the Higgs boson at collider, and that's why it plays a central role in our planning. And I just want to conclude with this. It plays a central role for future collider, and it's also a motivation for pursuing technical innovations in 2 areas. Accelerator, on how we get more efficiently to the next milestone, and as well as detector challenges in how eventually we can take the most advantage of that environment to properly identify all the particles. And thank you for your attention.
Thank you very much, Caterina, for the very nice talk. Questions?
Hey, yeah, thanks for the talk. I had a quick question about that slide where you had new data. Sorry, it's like, I don't know, so many slides back. But I'm just not used to looking at pictures like this. But if I just looked at the data points,
Which
and then
one?
The one where there was a slide that had a bump in a curve, and you said this is new data for.
Yeah, excellent.
yeah.
Yes, let me go back
Yeah,
at it.
yeah.
I have a way to see the slides without looking by one.
Yes,
by one
this
by
one.
Yeah.
Yeah. So maybe I was a little bit confused about how you're drawing these lines, because if I just look at the black points on this data, that does not look like a peak to me there.
Fair. If it was the first time looking at this plot, I would be not totally convinced either. So let me tell you a little bit of background how we get here. So this is the result of the analysis. So before we get to look and try to model this data, we do some test hypotheses about how the background should be modeled. And we know for simulation more accurately how, from standard model calculations, how the signal should look like. So the background here is mostly gamma-gamma plus jets, and gamma jet where one jet is faking to be a photon. So we don't have a really Monte Carlo that we can rely heavily on. So we use a combination Monte Carlo, knowing that the accuracy is not great, and data sidebands to really model the background. So then when we think we have done our job defining something we believe could be accurate enough to model our background, and we do some test hypotheses to verify there is no bias into it, then we do a signal plus background fit. So what you see here is the result of a signal plus background fit, where one of the parameter of interest we try to extract is the probability of the signal having the cross-section predicted by standard model for the sensitivity we have, for the data set we have here. So that's why you see a peak, because we are telling you need to fit me a peak, actually 2 peaks, because I also have the single Higgs background in here, and a continuum, and that's why it's returning that.
I see. Thank you.
Not yet. It's less than a sigma, so it's not very.
Yeah, thanks for the talk. I was wondering about when you showed and you mentioned it shortly for one of the linear colliders. I didn't actually know about the 2 detectors. Do I understand correctly that you would have like 2 detectors side by side on a movable platform or something? And
I don't think they would be side by side. It would be like literally one goes out, one goes in, like push and pull. Yeah. I don't know. So I think they have demonstrated they can do that. Let me go back to the image. Sorry. So I don't have anything about this in the backup. But basically, talking to the ILC people that have been like for years planning for 2 detectors that would be alternating with push and pull, it's something that you have your detector on rails basically, and then you slide it out, and then the other one comes in. So they are in the same cavern. They are just like on rails and shifting. And ideally, they say that they can, in one day, realign the detector and be ready for data the day after. So with very minimum downtime. Yeah, so do I trust it? No. But in principle, it's something that has been studied. I'm not an expert on that.
Yeah. Okay, this was leading a bit into my next question, but I understand if you're not an expert, but I was wondering, what do you think about whether this advantage of having an independent check with 2 detectors is worth the fact that each detector will only have half the data set? It's technically more complicated. You have to do more calibration, downtime, all these things.